Sorry.
Brilliant. Thank you so much. All right, so let's talk a little bit about BLISS. To help guide me, how many people have looked at like a listing file or BLISS source code in their life? Okay. How many people have written software from scratch in BLISS? You don't count. How many people have modified an existing, fixed a bug in the existing BLISS program? Okay, cool. So what I'd like to do, if I could, is waste a little bit of your morning. Let's talk about some history, which may help you understand why BLISS is the way it is. We'll talk about some details of the language, and then if we have time, I'll give you some extra credit, bonus, overtime information. So the reason we're here today, of course, is that a bunch of the operating system and the pieces of the operating system are written in BLISS. Starlet, the text libraries, there's .req files or .r32s all over the place. There's a lot of support for developing in BLISS. The compilers, certainly in the VAX days and the alpha days, were really, really, really good. BLISS, the language itself leads to being able to have optimized code. The compilers did a good job. A ton of the things you call all the time, libdollar, whatever, those are written in BLISS. So understanding and knowing BLISS, and it's such a beautiful language, and I'll badmouth C a lot. So the history, guy Bill Wolf invented this language because he wanted to write an operating system, and he wanted a language that was appropriate for writing operating systems. Originally, it was put together for the PDP-10, and although everybody, like I have repeated 1,000 times that BLISS is Bill's language for implementing, he said no. It was just sort of a random name that they came up with. I assume because it was perfect. I don't know if the next slide talks about this, but Bill was the first PhD of computer science at CMU. I mean, he is one of the luminaries of the industry, for no doubt. So why did he want to do it? Well, he wanted a language which was fast, powerful, had good style, high efficiency, could do coroutines and recursion and all of these things that in the late 60s, some of this stuff is kind of novel. I mean, this is not what you learned in computer science class. So what makes a good computer program, a good language for writing useful computer programs? Data structures. Digital used to have a whole class that they taught in Bedford, I assume, about data structures. Newth has an entire volume about data structures. It's the most important part of computing. Algorithms and stuff aren't that big of a deal for the most part. So lots of good control over the data structures, flexibility, modularization. Okay, we don't write 25,000 line COBOL programs any longer. We write modules that do things. And so we want to have a language which makes that a natural kind of, again, late 60s, okay, we're coming from Fortran and COBOL and assembler. That's our mindset. Okay, structure, understandability, flexibility, all goodness, okay? This was thought out. This was a designed language, unlike some others, which just sort of evolved. If you're old enough to have ever done any work in Algol, which nobody in this room is, BLISS evolved out of that understanding. It's very similar in look and feel and kind of the concepts. Okay, That's where BLISS came from. Now, how did it enter our lives? Well, in the early 70s, guy Ron Brender at Digital, this is early 70s. Digital is a young, small company. They have basically at that point in time 3 products, right? A 36-bit machine, a 12-bit machine, and a 16-bit machine. So he went to CMU, talked to Bill Wolf. They realized they had some common goals and some common understandings. Bill Wolf was also one of the, say, architects of the PP11, as I assume an advisory role. He also built a computer called CMPP, used an operating system that he called Hydra, which, and again, this is the 60s, you could add memory to a running Hydra machine and it would realize the memory. I mean, this was a modular, adaptable, I mean, kind of a big deal. But this relationship between Bill Wolf and Ron Brender evolved into Digital and expanded into 60 years of compiler development, language development, and operating system development. So the first projects were running on PDP-10s. Fortran 10 language was implemented in BLISS, and I'm sure there was just a little tiny bit of self-promotion involved here, but BLISS was the reason why Fortran 10 was successful. Probably had nothing to do with the fact that we had a Fortran compiler, but whatever. So that experience gave people in Digital confidence that BLISS had some legs. I mean, we can take advantage of this. So there's a whole bunch of activity, like pretty much from like 72 to 82-ish. A lot of activity. BLISS got renamed multiple times. The language got extended. We went from kind of PDP-11 based, became VAX based. The 36-bit world, as it was sort of mature by that point, didn't get as much attention. So back in mid-70s, the decision was made that BLISS was going to be, originally the slide said the implementation language, but then I recognized that's really not fair. So an implementation language. Of course, we still wrote macro 32 and macro 16 and God knows what else. So VAX BLISS grew out of the experiences of BLISS 11. Then, as all successful things in Digital did at the day, we constantly keep changing our names of an existing piece of functionality or software or an engineering team, so you think they're new. So BLISS 10 kind of evolved into what we call BLISS 36, 11 to 16, VAX to BLISS 32. So that's how we got here. Then somebody came along with a PC, and so we had 64-bit alpha BLISS, which we'll talk about why that had to happen. The Intel architecture, the GEM compiler backend, which was the underpinnings of all the compiler. You know, John will tell you the front end takes the language and turns it into some glop, and then you give it to a code generator and it turns it into a computer program. So GEM was retargeted to be able to produce code for x86 or for Intel instructions. The very, very successful DEC Fortran compiler for Windows NT was built on top of that. And then most recently, John will tell you all about at some other session, the BLISS compiler now calls another layer, which calls LLVM and produces stuff that we can run on modern x86 CPUs.
So what did the Intel 32 the compiler run on? What operating system did it run on?
Windows NT.
Just NT?
Yep. And that is, as an aside here, is how RDB was ported to Windows NT. And that was version 8.
Whatever release.
Nope. No, because the thinking inside of digital was that's going to compete with alpha. All right, so I like this slide for people that can read. Your computer science class, the prerequisite for the recursion class is taking the class. All right, so we talked about all that. You can download with a little bit of effort BLISS compilers to run on your TOPS 20 machine off the internet, in case anybody's still running TOPS 20. You know, I've scoured around. Big deal. I mean, I don't develop on PDP-11s very much anymore, but I could. So this is a real comment from a real results disk of a real OpenVMS build from a module. And it says this code takes advantage of BLISS language features that will overwhelm or intimidate a C programmer. And I think, you know, this is worthwhile to note. I mean, there is a tremendous amount of stuff that BLISS does, either in the macros and the precompiler stuff or the language itself. They're going to be very, very foreign to somebody who's a Fortran programmer. You know, I mean, the ideas that we're presenting here are advanced for certainly the late 60s. So why is BLISS interesting? Why am I wasting your time here? Well, in BLISS, it's an expression-oriented language, and we'll talk a little bit about what that means. It's typeless, so the language itself really doesn't understand things like data structures that contain bits and pieces and variables and long words. The language itself doesn't really get that. We've added all sorts of stuff to make those things happen. It's unique. We'll talk about the fetch operator or the dot that punishes people. There's no go-to in the language. And the compile time language or the preprocessor, the macro capability, it's not simple substitution macros like you'd have in C. This has an incredibly powerful compile time environment.
No, I don't think he should be in here.
I don't think either one of them should be in here. The border security in New Hampshire is very porous. All right. Good thing you didn't show up on time. All right, so key fundamental understanding here. In BLISS, everything, that's a tiny little bit of a lie, but it's not important. Everything has a value. Everything is an expression. An if statement has a value, a while loop has a value, and that's a big deal. You can do a lot of very, very powerful, damaging things because of that, and you can make code very unmaintainable by taking advantage of that. So we'll talk a little bit about how we do bad things. Because everything has a value. Just keep that in mind. This is an expression language. It is not a statement language. Okay, you know, Fortran basic, whatever. You do, not in BLISS. So here is an example of an expression. And so what we're doing here is we're saying the variable z equals, now I've got to begin an end block, which do what you think they're going to do. And I set temp equal to something, and I do some operations, whatever. And I say x equals y. And there's no semicolon here, so the statement's not terminated. So z, at the end of the day, is set to the value of that expression, which will be either 0 or 1. Very, very obvious to the guy who just looks at this, tries to figure out what the heck is z. So be aware of that. That's how things work. There are plenty of operators in BLISS. And I personally, and again, I spent many decades developing in BLISS. So when I use C and the equals construct, I have to force my brain to think, oh, that's EQL, you know, to make that translation. So we have equals, not equals, less than, greater than or equal, yada, 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 unsigned, and address. Address is really unused on the modern systems. That was a PDP-10 thing. Unsigned versus signed is important because the language doesn't have a terrific way of saying this is an unsigned integer. It's just a 32-bit value. It's a 32-bit thing. So my expression is where I describe that I want an unsigned comparison or signed comparison. So that's also a rich source of potential errors later on. The language itself, the unit of allocation, the unit of access is the native size of the word of the computer. So on BLISS 36, the native unit is 36 bits long. On BLISS 11, it's 16 bits long. And what was I going to say about that? That's why we have two separate compilers. So we have BLISS 32 and BLISS 64, because the nativeness of your computer program is based on the architecture of the computer. And of course, we have 32-bit computers and 64-bit computers, which are really a 64-bit computer. So the easiest way to get there was to have BLISS 32 and BLISS 36. So this is the crux of the C programmer's sorrow. Every other language in the world, if you say x equals y, the value of y, 127, is put into the x variable. Not in BLISS. That expression, x equals y, says take the address of x and put it into y. So if you're familiar with the ampersand operator or the IADDR language primitive to get the address of a variable, that's what you get in BLISS. That's how it works. And so it's the opposite of using an ampersand, which again is going to lead to a lot of sorrow. And so if I say x equals y plus 7 with the dot, I take the value of whatever is in y, add 7 to it, and store it in x. If I forget the dot, remember I've got a 5,000 line module here, and there's one missing dot. So now it takes the address of y, adds 7 to it, and puts it in x. Not what I had wished for. Dots can be put all over the place. So I can have a dot on either side of an expression. I can have dots within expressions. So here I take x, add the value of q, fetch from that memory address, and add 3 to it. And this is why young programmers learning BLISS for the first time aren't very effective, because they spend their entire afternoon adding and removing dots until the access violations go away. But you can do really cool things, like x equals dot dot y. So fetch the value of y, which as it turns out is going to be a pointer to something else, and then fetch the value of that and put it in x.
To be fair, I've seen C programs that say x equals star y.
Fair, agreed. And the Fortran guy?
No.
All right, so when we first got alphas, they were the same as the VAX, right? It's a 32-bit machine. Pretty much everything was the same because all the effort was spent making VMS work on it. A little bit later on, VMS on Alpha became much more 64-bit aware. We were able to take advantage of 64-bit addressing and access quad words much more naturally. And so the BLISS 64 compiler came along to make all those things happen. Unfortunately, over the years, many thousands of lines of code were written with a lot of knowledge about where they were running. And where they were running was a VAX. And so a construct like this, foo $L next, probably a singly linked list. And so this data structure component points to the next thing on the list. And so a clever developer somewhere along the way said, well, if I dereference that twice, I'll get the thing that I'm looking for. I know my data structures, whatever. So on BLISS 64, however, it's not going to do the right thing, because I'm going to fetch a quad word from the second dereference, and bad things will happen. So that was a painful transition for, I definitely abused the knowledge that I had about the computer, and so was punished for it later on. Okay, data storage. Pretty much like every other language in the world, you can have module local, you can have module global, you can have routine local, heap storage, or not heap storage. You can have persistent storage for routine, or you can have storage on the stack. Pretty much all that stuff works the same way as all the other languages. I don't need to tell you about languages. The fundamental integer storage types, words, long words, bytes, quad words, whatever. Pretty obvious how all that works. Vectors are arrays of words, long words, bytes, or quad words. Pretty straightforward. Bit vectors, as the name implies, is just treated as an array of bits. A block is a description of a complicated data structure, if you will. And then a block vector is a whole bunch of those. So kind of familiar, if we think about other languages, C in particular, do all these things with slightly different names, except in C, it's not possible to access a bit, no matter how bad you want to. Big deal, vectors, yada, 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 bit vectors. Bit vectors were heavily used in some of the projects I worked on. A bit vector was a very common thing. You just had a whole bunch of flags, and you just look to see if they're set or clear. Block sequence of components, and block vector, a whole bunch of those data structures. I think I've got some examples. So initial and preset are how you specify an initialization of a data storage, or a variable, if you will. So it's sort of like in C when I'd say int x equals 0. So x will be initialized to 0 on the stack. Same thing with initial, but I can initialize any of the members of my stack and this and that and the other thing. If I don't say it, okay, yada, yada, yada. Preset is similar to initial. If you get to the point where you're struggling between using an initial or a preset, just come ask John or I. It's not worth explaining the differences. Okay. Spend a few minutes talking about this. So what happened? You trip on the cord? Did I? Okay.
Reboot crash.
I crashed the projector. Oh, okay, so when you reference an element of pretty much any data structure, you reference it by its byte offset, its bit offset, how big it is, and whether I want to sign extended. So instead of just being able to say, you know, struct, foo, all these elements, integer, you know, whatever, char of 64. So if I'm just going to reference a naked quad word, okay, with no other ancillary stuff, its byte offset is 0. It is at the beginning of my data structure. Okay. Its bit offset is 0. It's the beginning of that byte. It is 64 bits long. And I'm not going to sign extended. Sign extended to what? I don't know. But I'm not going to sign extended. As opposed to some other data element that starts at byte 3. It's at the second bit of that byte, and it is 1 bit long. Now, obviously, this is super easy for human beings to deal with, and you'll spend a lot of time for that to become obvious to you what it's doing. But that gives me huge amounts of power when I describe my data structures, because having a 3-bit field in the 7th byte of a structure halfway through the byte is cake. Easy to describe. I don't even need to know when I'm writing my program what it looks like, unlike some other languages where I have to mask and shift to get that data back. So here's a real reference from a real data structure, and all of these are macros. We've given, just like in C, it's a simple substitution macro. We have a string that's going to be exposed. So the macro IRP$V_buffIO is offset 80 in the data structure of an IRP, so 80 bytes in. It's at the first bit, and it is 1 bit long. Oh, this is a flag. What's the flag mean? Well, I look at the listings and buffered IO flag. These are bits. I'm grateful for the engineer that figured that I wouldn't be able to understand a flag was just a single bit. The function is the next bit in that byte, and it's also 1 bit long. So this is how, like, things in starlet or lib.req are expressed to BLISS. And so when I reference, you know, .myrp bracket IRP$V_virtual, I'm really just referencing that bit in that byte. That's how this happens.
To be fair, I comment these bits must be adjacent in order. Somebody else somewhere grabs those bits 3 at a time. Right?
Oh yeah.
And there's no indication from here. I can see you might have a union or something to infer that sometimes these bits together are also useful. There's no hint of that. Just
Look,
you know.
if it was hard to write, it should be hard to understand. So the other thing you'll see within code, for like the next level up of sophistication, if you will, is the angle bracket syntax, where I have an address of something, and then I specify right inside the code the bit position, the size in bits, and if I want it sign extended. So I don't have the offset from the beginning of a data structure. I know that that it's beginning at address. You know, it's beginning at this particular memory address by some variable. Grab me these bits at this location. And you'll see this with with other kinds of macros as well. Bind gives something another name. And so bind and map are sort of like giving things other names and other attributes at different times. It's kind of shorthand, avoids me to have to replicate a whole bunch of stuff. It's conceptually similar to, you know, I come into a routine, I've got a C data structure that has a whole bunch of other structures inside of it. And so I'll just call one of those data structures out by name and have a type associated with it, and I can access it that way. Bind is a tiny little bit significant, if I remember properly, because it is conceptually bound at the point of declaration, as opposed to the point of use. Map is just changing the attributes of something, and that is effectively bound at the point when it's used or expressed. So change names, change attributes of existing things. So this came out of real code, which I can't remember what code this was. But we take a universal identifier and we convert it to base 32. And so I call create UID, which gives me this 128-bit unique identifier across the whole world, or at least in my cluster. And then length is set to length, the literal length is 1 plus 16 divided by 8, divided by number of 5 bits per character of the output. And I just go into a little loop here, and I bind temp is the value of the UID, this position, and this number of bits. So I just go through this 128-bit array, 5 bits at a time, and then this delightful code here adds a or 0 to convert those 5 bits to a alphanumeric. Very, very elegant. Wish I could remember where this was. All right, flow of control. So back in the late 60s, there was a couple of computing luminaries, including Dijkstra, or however you pronounce that in Dutch, badmouthed goto. The use of goto, he thought was an aberrant offense to all of computing. And so he wrote a letter to the ACM Communications, and Nicholas Wirth changed the title of the submission to "Goto statement considered harmful." Then Don Knuth said Dr. Goto cheerfully complained that he was always being eliminated. These are like the brains of modern computing languages making fun of each other in public. That's so cool. Yeah, how unsocial and uncivilized they were. This is a big deal. Like Java is just about the only other language around that there is no functional go-to. This was a big deal. I mean, we were breaking ground here. We're no longer Fortran and COBOL programmers. So because of that lack of go-to, we had to have lots and lots and lots of other ways to change the flow of control in our program. We have while loops, until loops, if then else, pretty standard. Incrementing and decrementing loops, cases, sets, which are, yeah, I'll badmouth C later. Return, we can signal things, we can leave blocks, we can exit loops. So there's quite a variety of things you can do here. I was taught early on, use as few of the different ways possible as you can to get the job done. because it makes for a lot easier to understand code. So if you're familiar, the alpha computer and the VAX computer both have instructions built into the computer to say, is the least bit clear? Branch or don't branch. And I always thought that was sort of odd. Like, why go through all the effort to deal with odd and even? Yeah, negative and positive, yeah, that makes sense. It's because of BLISS. Because an odd value is success and an even value is not success. And if you look at all your status codes, SS dollar, whatever, ACVIO is odd. SS dollar normal is even, or the other way around, is even and odd. It's because of this. Because the BLISS language said, if something is, the low bit is set, it was successful. If the low bit's clear, it was a failure. So anyways, that's another little tidbit. The other funny thing here about BLISS, and is foreign to a C programmer, and I got burned a lot when I was learning C, is because in BLISS, the order of evaluation inside of an expression is not defined. The compiler will try to figure out what's the best way to do this operation. And so here in my example, I have if.a or f.b. Function f might or might not be called, but I can't tell when I write my program, because this might or might not always be called. This might or might not always be evaluated. So there's no implied or expressed order of evaluation. And we get around this. I'll show you some other examples later. You use cascading ifs and elses. In Fortran, is that true?
Yeah, there's no defined.
Okay. But in C, that expression will be evaluated left to right and we'd shortcut out. So be aware of that if you're naively translating some of this code into C, it matters.
The 1-0 thing in C, 0, non-zero is the thing that'll really catch people converting BLISS to C, because it's not the same comparison.
Yeah, does that make sense what John said? So in C, an expression is true if it's non-zero, and 0 if it's false. In BLISS, it's just odd and even. So if you take a naive translation of that, it's not going to work right. Yeah, so SS dollar normal in C is true, but so is SS dollar ACVIO. All right, so the case and select are my two favorite language constructs that I desperately wish C would learn how to do. So case says find all of the expressions, or evaluate all of the expressions until the first one that matches and do it. So it's C select case with a break. The select expression keeps going. So it picks every one that's true and executes that expression. So what I can do is I can have a flags long word, and I can say, find me the ones that are true of this, or this, and execute the corresponding action routine or whatever it is. So it's like C without the break statements, but it does the right thing. Here, if F1 and F4 are true, I'll execute R1 and R4, but the intermediate ones are not true, so they don't get executed. I'm so frustrated by C's lack of this. Now, Pascal presently can do all that stuff. And then select one works the same way, but it stops the first time I get to a matching expression. Increment and decrement, I have to admit, I kind of sort of a little bit like C's for loop construct compared to having to do it this way. But it's just working your way through an array, you know, for I equals 1 to 10, approximately.
But you know, user specs, these are expressions. You say checker, check pointer from begin 8 pages of code.
And no semicolon.
No semicolon, but you'll never be able to match it up in your human brain.
Yeah.
We're supposed to.
Yeah, I mean, the point here is these increment and decrement loops have a value as well, depending on whether you throw away the value with a semicolon at the end. And most of the time, the compiler can tell you this isn't a good idea. All right, declaring routines, pretty straightforward. Give it a name, parameters, and inside I have a local variable on the stack, yada, yada, yada. Thanks to John for this one. This is real code in a real operating system from a real company that we're familiar with. So there's a missing semicolon here. So this loop exited prematurely, unexpectedly. And I don't remember all the details, but it's really not all that important. But finding bugs like this is a mental challenge. Yeah. I mean, this is non-obvious.
What's the value of this statement?
What was the bug here? I think the flaw here.
Well, we exit the loop with a value, but you're right. I mean, in the case of not exiting the loop, you don't get the increment.
Yeah.
Right? If you only do exit, you get the people one on your way out to the while, which no one cared about, but you don't get the increment, the non-exit loop path. It's a cut down version.
It's the problem is this is vastly too simplified from what is really going on. But yeah, this is a bad example.
Sequence value one blah blah blah. In the value of x. Exit loop does cover the value.
Yes. So here, what this is saying is exit loop of the value p. So p equals p plus 1.
That's the expression.
That's the expression. So we incremented this one too many times.
But then what is exit loop when you don't give a value? I think that false true might be a difficult one. I don't know if it's exit loop. If I just did the exit loop, what's the value of the while? This is expression something.
Yep.
I take it. I think it's true.
It's got to be, yeah. How about this? It's either true or false.
One of
I'm real sure.
the other real world example I had was somebody had a comment somewhere and they forgot the exclamation point. The line actually just was a minus. So they wanted to say exclamation point with a dash after the comment. And so just a minus. And then the next page or a line close later, you get A equals 1. Well, what you really saw was negative A. And West's the address of A inverts it, and whatever that address was,
Tries to store.
the assignment statement is take whatever values on the right and assign the memory location on the left. And I'm not sure where it will be. They put it in a really bad spot.
Almost for sure it's not what you meant. All right, so real quickly, we'll go through the sort of the compile time or the C preprocessor methodology. Mostly the percent sign is going to be associated with something that happens sort of at the compile time language, which is similar to the BLISS language, but not the same. But we have ifs and else's. We have lengths remaining, declared switches. There's quite a bit of complexity here. Bunch of lexical functions. And again, these are all compile time things that before the language gets involved. Percent ref is kind of cool because it's sort of like using ampersand 7 in C, like give me the address of a literal 7. %ref does that here. These are much different things. Saying f of x, so that's called function f with the address of the variable x. Here I say call function f with a pointer to a copy of the value of x. So you're getting different things. If you're writing complicated macros and you need to like redeclare things and do all this gross stuff, quote and unquote will become your enemy and your friend. They're your enemy until you make it work, and then they are your friend because it makes it possible. So we can, so here in this conceptual example, there's a macro called fancy, and then I have to get rid of fancy. But if I say undeclare fancy, fancy is going to get expanded and become this, which you can't undeclare a function call. So I say %quote to avoid that expansion. It's gross. All right, let me give you a couple fun examples. Macros are recursive, iterative. I mean, everything that you can do in your brain can be done in macros long before you ever get to your program. There's enough, yeah, I mean, so here's one of like what I do. So I've got a macro check error sig, okay, and I've got some expression. I bind the status variable to the command. I use a bind so I know that it can only be executed once. Because if I didn't, then I would execute the expression here. And if it failed, I would execute the expression again, which is, if it failed once, doing it again is not going to make it better.
It had a function call.
Well, if it had a function call, but then you're really in trouble. So anyways, so this is how in my BLISS code, you see this all over the place, I check status. If it didn't work, signal stop, it's over. Here's an iterative macro that builds the values of a table. Again, we're not going to bother to go through it, but the magic here is this %remaining, which in effect peels the first thing off of the list of variables and then gives me all the rest of them. So I can keep calling myself, and I just process the first element in the list and call myself again with all the remaining.
I could say lists could, but no one was listed.
Has anybody had to program in Lisp? How about APL? Did you use the special keyboard? Okay. So here is an example that goes back to the order of expression evaluation. And this is used all over the place. So I have a macro or some variant of it called all true, which is conditional and iterative. And so what I do is I take the first bit of the expression that's given to me and I evaluate it. If there's any more, then I call myself again with the remaining part of the list. And I think I have an example of how we use that. And so this comes right out of lib.req. Whoever did it, called it and then. It's the same as my all true. But you give it a list of expressions and it evaluates them one after another until the first one is not successful. And so I force the order of evaluation here. Somebody says if the block pointer is not 0, then if the flag is set, then do something. And the idea here is don't dereference a null pointer because there's nothing to dereference. And these can become very complicated. One of my coworkers at a different company I work for learned about all true and used it for everything. Like anytime he would this or this or this or this and this and this, even if the expression order didn't matter, he said, Mike, you know, this is a special case. You force of order evaluation, but there was no changing. Okay, so when you're programming in BLISS and modifying existing code, you're going to see macros like $QIO. If you open the system service reference manual, there's going to be references to $QIO. So $QIO is a macro where all of these names are declared. And what I can say is, for example, AST adder. So if I use the $QIO macro and I specify, you know, the channel number, the function code, and the IOSB, we always use IOSBs, but I don't specify the AST adder, it'll become 0. And that macro expands to sys$QIO, which is the actual name of the system service, with all of the parameters described up here with the default values taken. So that's how $QIO looks like it's a language thing, but it's really not. It's just a macro. Here's a little macro that I got from somewhere that disables ASTs for some operation. Like maybe I don't know, doing something that has to have ASTs disabled. So what I do is I say, I give myself a local variable. I call set AST, turn ASTs off. I execute whatever this expression is, something that can't run with ASTs enabled. And then I turn ASTs back on and I return the status of the expression, the routine that I called. Does anybody know what the bug here is? So the bug here is that I never set ASTs back to the state they were when I got here. I always turn them back on, which also a very difficult thing to debug. You don't care about that. Built-ins, any one of the magical things that your computer can do, breakpoints or the PAL codes for removing queue entries or the VAX instruction for me, all of that is hidden inside of built-ins. They're muchly upward compatible. The real common ones are going to be on x86. The VAX specific ones might or might not be, depending on if it was needed in VMS and encapsulated in some RTL routine or some other primitive. You don't care about any of those. Character functions, very similar in concept to the C runtime library things that move strings back and forth and fill blocks and stuff like that. Yeah, we're not going to spend a lot of time there. Who cares? CH move and copy go right back to the VAX instructions, move C3 and move C5. Who cares? If you're doing floating point, don't do it in BLISS. You can make it do a lot of things, but it's not a good idea. The export library uses all sorts of combinations of %BLISS to figure out what kind of BLISS it is, and it is possible to modify it to make it work. You don't care about linkages or PSEC switches.
Oh, we care about.
Demand 0 only, not allowed otherwise. So here was making fun of Itanium when this was originally written. Okay, you don't care about that. All right, SDL, my last topic, I'll go real quick. SDL is structured definition language, and it's a language independent way of describing data structures. It would not be possible for human beings to write good BLISS code if it wasn't for SDL, because all of our data structures would be unbelievably simple. But you can get it for many of the architectures and platforms. Starlet, lib, all the .req files probably came from SDL. It can produce Fortran definitions and C definitions and BASIC and probably languages which don't even need PL1. Anybody? So pay attention to what SDL does if you're developing code, like if you're working in, the lib facility or whatever, you'll need to know this. Who cares? BLISS. Export library was a bunch of macros that was really heavily used. And when done well, you could take the same bit of code on TOPS 20 and PDP-11 and VAX, and it would just run because the export library hid all of the complexities of operating systems. It's been grossly neglected. So be it. All right. I wasted your hour. Thank you guys for coming. Thoughts, comments, questions? If you happen to work in or near VSI and like you find yourself programming in BLISS and you're frightened, John is an excellent tour guide. We'll help you along your path. There are some engineers today that prefer to ask me questions so they don't have to talk to John. All right, have a good lunch. Yes.
What made the seed in standard language for system programming? Is the seed better or it was marketing issue?
So why do we use C?
Yes.
Is that the question?
Instead of BLISS.
Because it was free and they didn't want to charge for us. The only reason, in my opinion, the only reason Unix and C are popular, it's not because they're good, it's because they were free. That's the only reason. I mean, C has a lot of, C does a lot of things really well, and it's a great way to write programs rapidly. They're reasonably well understood. A lot of people that do it, but for me, in terms of implementing an operating system, I like BLISS.
And also, originally part of this point is that, very first BMS charge, C wasn't available when BMS v 1.5 came out, but macro, we've always bundled macro for free in the operating system. Some people thought we should charge for macro. On native one, I get that, like native alpha macro, Macro 64, the native alpha macro for some work was up there. I could have paid.
Yeah. And no other company besides digital really adopted BLISS at all. So BLISS is pretty much DEX specific. Yeah. No other company ever put. So it never had any adoption.
Well, the person who wrote trying to see about that CPM base was also some product. That might have changed.
Yeah,
CPM version.
I would say that is really the answer to the question. Had BLISS been given away, had VAX has been given to all the universities with BLISS on it for free and charged for the other languages, universities would have taught BLISS.
That's why we're special.
The basis of the lack of data science, lack of point, and the lack of any standard library.
Yeah.
No print. In C at least you have fopen and printf, and those have a formatting things, and those are platform independent. Printf in theory works on every place, and C works. BLISS doesn't, and that's where this whole export package came from. It gave a somewhat standard way of doing I/O, for instance, that never existed anywhere else. No one ever, even in BLISS, no one uses export. Well, almost no one uses export for I/O.
Yeah.
I want to see a good example of export with the runoff sources. and I put good in quotes. It does use export. Runoff is part of the biggest user of export.
Yeah, well, that's from the buffer file.
Because something runoff exists on TOPS.
Yes. Why don't we have a Ada compiler on x86? 7 people in the world develop data programs. That's the answer to that question.
But they're wild.
So go home and write a BLISS program on VMS.